And the problem I have explained before is that the controllability is an issue. Okay. So, it is difficult to control the state to any known value. These are the primary inputs, these are the primary outputs, this is a combinational logic. Similarly, the observability of these next state information is also a problem. Okay. So, we talked about controllability and observability. So, a very standard solution for this problem was proposed in IBM many years ago. Okay. It was called scan design. Okay. And now it is a very standard solution, industry uses this, right. So, the idea of this solution is that see, the state register, okay, is a parallel in parallel out register, right. So, this is a parallel input and this is a parallel output. Okay. But you may be able to redesign it to be a serial in serial out and a parallel in parallel out register. Okay. In other words, there is a control signal. If that control signal is 0, it acts as a parallel in parallel out register. If the control signal is 1, it acts as a serial in serial out register. So, let us redesign it like that. So, suppose I have a state register, it is a parallel in parallel out. So, the next state guy comes here and the previous state comes here, but we also have a serial in serial out. Okay. And this is my combinational logic, and as before this guy goes here and this guy goes here, and this is my primary inputs and this is my primary outputs. So, there is a small change in the register. So, let us assume that there are n bits here. Okay, that means there are n flip flops. So, what is the essential idea in this scan design, right? When you want full controllability on the state register, that means you want to initialize it to any value. To initialize the state register, to some value, okay, what we do is we remember I told you there is a control signal. Okay, we will call it as scan enable. Okay. Set scan enable to 1 and that makes it a serial in serial out register. Okay. Then then you can shift in the required state into the state register. So, in a way we are going to do a little bit of cheating, right. So, if my test vector requires me to put some arbitrary state, let us say 1 0 1 1 0 1 or something like that, then I am not going to worry about how to get that functionality of the state, I am sorry, functionality of this state machine to get you into that state. I am going to simply cheat and I am going to shift in that value, okay, that particular state through the serial input. Okay. So, this will require n clock cycles. Okay. So, unfortunately, it will be slow, it takes a lot of time to shift in the required state. Then we go into the mode where scan enable is 0. Okay. During that time, the it will act as a parallel in parallel out register, okay, and you can capture the next state to state register. Then you may want to see what is there inside the state register, okay, whether it went into the right state. Okay. See, for example, our test vector, let us say I am trying to test for a stuck at fault here, then it may, if I look at this combinational logic like this, my requirement may be that I must put 1 0 1 1 and maybe some other arbitrary state. This is a state that I need to send it to, okay. And then it says the output should be 0 1 1 0 and the correct state should be 1 1 0 0 1 1. Okay. Now, how am I going to do this? Initially, I am going to set scan enable to 1 and then this particular value will be shifted into the state register. Then I am going to apply 1 0 1 1. So, that will activate the fault and propagate the fault to one of these places. Now, I have to go and check whether this value is there in the state register or not. For that, again I go back to the scan enable equal to 1, okay, and I will shift out the contents of the state register, okay, shift out the. So, it is shifting the state that you want, then do a capture to capture the next state into the state register and then shift out the contents of the state register, and then you can compare and see whether 1 1 0 0 1 1 is present or not. So, as you can see, it is going to be slow, right. We will need n clock cycles to shift in the previous state, 1 clock cycle to capture and then another n clock cycles to shift out. Okay. But the advantage we get is now we can overcome the controllability and observability problem. Okay. We do not have to worry about controllability and observability. Okay. So, how do I design the register? How do I redesign the register to be a parallel in parallel out or serial in serial out? Depending on a control signal. Okay. So, remember how we designed a register, right? So, we took a D flip flop, we had a clock and a reset, D and Q. So, we took a lot of these guys, the reset was connected everywhere and the clock was connected everywhere, right, and maybe we called it D2, Q2, D1, Q1 and D0, Q0. Okay. So, this was the parallel in, and this was the parallel out. Whereas, when we want to do a shift operation, that means we want to shift in the contents, so you can see that if this is the previous state 2, previous state 1 and previous state 0, we also need to be able to shift in the serial in directly. So, we will need to have an ability to either take the PS2 value or the SI value. Okay. So, that is done with the help of a multiplexer. So, we will put a multiplexer here. Okay. And so, this is my 0 and this is my 1. That means, there is a control signal. If this control signal, which I call as scan enable, if it is 0, then it acts as the PS2 is getting shifted into D2. If it is 1, then the scan I am sorry, serial input or scan input is shifted into D2. Similarly, I may need multiplexers here also. So, I will have to put a multiplexer here, okay, and this guy goes here to the 1 port, and to the 0 port I have the usual PS1 coming in. Okay. So, PS1 comes in there, and the same thing happens here. So, this guy comes here. So, this is port 0, that is PS naught is coming here. Okay. So, when I am setting SE equal to 1, okay, this scan enable has to be connected everywhere. No? This scan enable goes to all the flip flops. Okay. When scan enable is 0, then it is normal operation. Okay. That means PS2, PS1, PS0 will become NS2, NS1 and NS0. When SE equal to 1, we call it as a shift operation. Okay. Some people will also say scan operation. So, we sort of scan the, so what will happen is serial input will go into Q2 or NS2, then NS2 will go into NS1 and NS1 will go into NS0 and then NS0 will go into that serial out. Okay. So, I will have to think of additional pins. What are those? SI is an additional pin, SO is an additional pin and SE is another pin. Scan enable, scan input, scan output. Later we will see that sometimes we may require another scan clock. Okay. But right now let us pretend that it is the same clock.